Again, and thank you for joining us on today's webinar, Best Practices for Proving with Coriolis Meters. I'm Allison Sterling, Marketing Manager at Emerson Micromotion, and I'm pleased to welcome you to our Emerson Flow Expert webinar series. Before we begin today, I'd like to take a moment to acquaint you with your webinar environment. On your screen, you should see a presentation window on the left side, a Q&A chat window in the upper right-hand corner, media player controls, and a resource box with related content that you can view and download during the event. You can resize, move, or minimize any of these windows during the event to fit your viewing preferences. At the bottom of the display, you should also see a row of icons that give you added capabilities where you can share the webinar via social channels or request a visit from one of our Flow experts. Throughout our presentation today, we encourage you to interact with our speaker by typing in questions and comments using the chat panel. We will be answering questions both live during the event as well as after the presentation. We are recording today's session, and we will make the link of the recording available to you 24 hours post-event via email. On today's webinar, we are lucky enough to have joining us Mark Butler. Mark is our Oil and Gas Midstream Industry Manager at Emerson Micromotion. Mark holds a bachelor's degree in mechanical engineering from the University of Colorado. Mark has been with Emerson for a total of 28 years in a wide variety of roles and has specialized in custody transfer applications involving both gas and liquid products for much of the time. He is active with the API Committee on Petroleum Measurement and has worked previously for the NIST Office of Weights and Measures and remains active with the National Conference on Weights and Measures. In his free time, Mark enjoys traveling, hiking, biking, and skiing. Welcome, Mark.
Oh, thank you, Allison. And hi, everyone, and thank you for joining us today. We're going to start out by quickly reviewing some of the fundamentals of meter proving and some of the well-known challenges that we face when proving meters. Then we'll talk more specifically about some of the unique best practices that can make proving Coriolis meters easier in custody transfer applications. We will cover important considerations for sizing both the meter and the prover, and we will also get into some of the important details that will aid in the ongoing successful operation of the measuring system. So proving is a critical step to ensure the confidence of all parties that are engaged in custody transfer of liquid products through a metering device. Essentially, proving is using one measuring device to check another. A prover is a device that is used periodically to check a meter or a set of meters. A prover is calibrated periodically against traceable reference standards, and it is designed to remain accurate for a long time. So by testing with the prover, the meter's traceability is linked to the higher standards. The prover is only used part of the time, and this helps to protect it from metrological drift due to wear and tear. The meter, on the other hand, is used constantly to measure all the fluid product that is being traded. Many meters are expected to wear out and drift over time because of constant wear and tear. The prover in some cases acts as a maintenance tool because it can provide clues as to when a meter is wearing out and may be ready to fail. Coriolis meters are somewhat different from other types of meters in that they typically do not wear out or fail or drift over time. Nevertheless, the main reason that proving must be done on custody transfer meters of all types is to protect against the financial risk of measurement error. Normally, financial risk is the main factor that decides how often proving must be done. Therefore, the value and quantity of the product that is flowing determines how often proving is done. In cases where the flow rate is high and or the product is expensive, proving might be done before and after each and every transaction. Take, for example, the estimates shown in the table that show that 0.1% of measuring accuracy can be worth thousands of dollars per day. The table also shows that it only takes 20 or 30 minutes for an amount of crude oil that is equal in value to the cost of a large Coriolis meter to flow through the meter. In other applications where the value of the product that is measured is smaller, the proving might be done less frequently, perhaps monthly, to avoid wearing out the prover too quickly. Some applications are scheduled to prove whenever a certain fixed amount of throughput has passed through the meter. Another factor that might impact this decision is the type of meter and whether it wears out quickly or not. So there are two main categories of provers in use today: static and dynamic. Static provers are characterized by filling up a tank with liquid to a point and then stopping to take a measurement while conditions are stable. This measurement can either be a volume measurement with a calibrated volume test measure or a mass measurement with a weigh scale or a load cell. Dynamic provers are far more common than static provers, and they tend to fall into one of three types: small volume provers, pipe provers, and master meter provers. Proving can be done in either mass flow units or volume flow units. To prove a meter that is measuring in mass flow units with a volumetric type prover, it is necessary to determine a precise density at the prover and a corresponding density correction factor so that the traceable reference volume of the prover can be converted into mass units to compare with the mass flow meter total and thus compute a mass flow meter factor. I'll explain what a meter factor is for those who are unfamiliar in just a bit. The density correction factor for light hydrocarbons is usually determined using a pycnometer like the one shown below. A pycnometer is just a container that has a very carefully calibrated volume of space inside. To come up with the density correction factor, the pycnometer is filled with a fluid sample and then weighed on a scale. The tare weight of the empty pycnometer is subtracted from the measured weight of the full pycnometer to determine the weight of just the fluid sample. Then, the weight of the fluid sample is divided by the calibrated volume of the pycnometer, and you have your fluid density. Because the pycnometer can only measure discrete samples, it is used to calibrate a very accurate density meter like a Coriolis meter shown in the picture. Then that density meter is used to measure the fluid density for all the proving runs that follow. Coriolis meters can measure in either mass flow or volume flow units, so it is very common to find a Coriolis meter measuring in volume units. To measure in volume units with a Coriolis meter, there is no need for a pycnometer because a volume prover is used to directly determine the volume meter factor for the Coriolis meter, just like it would be for a positive displacement or a turbine meter. In fact, the volume meter factor will remain the same for the Coriolis meter no matter how much the actual density of the fluid changes, unless there's something wrong with the Coriolis meter. If you see the volume meter factor for a Coriolis meter vary by more than normal statistics would predict, you should call a service agent to look at the Coriolis meter. An approximate average relative density of the fluid is still needed in order to look up the correct volume correction factors for the fluid from the API Manual and Petroleum Measurement Standards, or MPMS, Chapter 11 tables. But this is not the same as measuring density precisely for the purpose of converting from volume to mass, and it does not require anywhere near the accuracy of a pycnometer for this purpose. When using a static volume test measure, it is important to keep careful records of the pressure and temperature of the fluid at the meter and the test measures so that proper adjustments can be made for expansion and contraction of both the fluid and the prover. Operators of static volume provers must also be careful to account for fluid clingage to the inside walls. Initial wetting of the prover and careful timing of draining cycles is used to account for clingage, but this is one reason why static volume test measures are not used very often to test with highly viscous fluids that would cling to the inside walls for too long in between tests. A mass measurement with a tank on a weigh scale is called a gravimetric method, and it does not require any compensation for expansion and contraction of the fluid because the total mass of the fluid test quantity remains constant, even as temperature and pressure change. Small volume provers are often called compact provers, piston-type provers, ballistic provers, or captive displacement provers. These provers consist of a short cylindrical chamber with a piston displacer that slides from one end to the other during a test. The total volume that is displaced as the piston travels between two detector switch locations is very accurately calibrated, and that volume serves as a reference standard. The displacer has a poppet valve that allows flow to pass through the piston when it is not measuring a run so that the displacer can be retracted and prepared for the next run. When the poppet valve closes, the piston must travel along with the flow and no fluid can pass by the displacer. Before any flow from the meter is counted, the piston must travel from the launch point to the location of the first detector switch. This is known as the pre-run. As the piston continues to travel past the first detector switch, the flow computer begins to count the pulses from the meter that represents the volume flow, and this continues until the displacer passes the second detector switch. At this point, the pulse counting stops, and the poppet valve opens so that flow can resume through the displacer as the piston stops and is retracted into position for the next run. The volume represented by the pulses that were counted is compared to the calibrated volume of the prover, and this is how the volume output of the meter is tested. Some types of small volume provers have the ability to select the location of the detector switches so that the pre-run time can be made longer or shorter by giving up some of the volume from the actual run. A pipe prover, sometimes called a ball prover, is very similar to a small volume prover, except that the displacer is a sphere or a ball that slides through the pipe from one end to the other. The ball does not allow any fluid to pass, so just as with a small volume prover, the reference volume is measured when the displacer ball passes by two detector switch locations. And the volume between those two locations is very carefully calibrated against higher reference standards. If the ball is returned to the starting point through a bypass, then it's called a unidirectional prover. However, the pipe prover will often have a four-way valve, as is shown in the diagram in the upper left corner, so that the flow through the prover can be reversed and the ball can be sent back and forth through the calibrated volume of the prover. This very common method is called a bidirectional prover, and it is a simple way to return the ball to its starting point. Data is collected in both directions, and each run consists of the total volume of flow during both the forward and the backward trips of the ball. The biggest difference between a small volume prover and a pipe prover is that the total reference volume inside a pipe prover is usually much more than the volume inside a small volume prover. Two consequences of this difference are that the pre-run time and the run time for a small volume prover are typically very short compared to a pipe prover, and a pipe prover generally occupies considerably more space than a small volume prover. Pipe provers can be designed to handle almost any flow rate just by changing the diameter and/or the length of the pipe. A master meter prover is simply another flow meter that measures the reference standard volume or mass total. The requirements for master meter proving are well documented in the API MPMS Chapter 4.5. The master meter is trusted because it is checked frequently against a higher reference standard. There are two different types of master meter proving, direct and indirect. In direct proving not with a master meter, the prover is located either permanently or temporarily in series with the line meter as shown. All the flow that passes through the line meter is directed through the prover during proving. In comparison, a direct master meter proving uses both a master meter and another type of prover that are located in series with the line meter as shown in the second diagram. The prover checks the master meter and creates a master meter factor that is then used by the master meter to prove the line meter. This approach ensures that the master meter is always checked in the installation and on the process fluid at process conditions before it is used to prove the line meter. The prover and the direct master meter may either be permanently located at the site or mobile. In indirect master meter proving, the master meter is located in series with the line meter, but there is no other prover at the location. Instead, the checking of the master meter against a prover is done in the indirect master meter method by periodically removing and sending the master meter to another location for checking, usually a laboratory. One advantage of indirect master meter proving is that a Coriolis meter can prove another Coriolis meter in mass units without the need for a pycnometer, because both the line meter and the master meter are reading in mass units, and the master meter would have been checked against a gravimetric or other mass-based higher reference standard. Master meter provers have not always been considered to be very reliable, because they often use only PD and turbine mechanical meters that could wear and drift over time. For this reason, it has been critical to check PD and turbine master meters against a higher reference standard very frequently. Indirect master meter proving is also difficult with PD and turbine master meters because they can be affected by changes in the fluid properties and the process conditions. However, master meters are growing in acceptance worldwide because Coriolis meters are able to perform very well as master meters with their design that has no moving parts and which does not drift over time. One nice attribute of a Coriolis master meter prover is that it is possible to collect pulses from the line meter for as long as possible or as long as desired, because there is no fixed volume that limits the length of the proving run like there is with a small volume prover or a pipe prover. So I'd like to pause now and ask a poll question. This is where the audience can participate by selecting the type of prover that you choose to operate most often. Please pick the one that you would use most often and then submit your answer by clicking on the Submit button. After everybody's voted, we'll review the results of the survey together. All right. So it looks like probably the most common is the small volume prover, followed by the pipe prover and master meter provers, which are actually in a close tie for second place. Static tank provers are used less frequently, as you might predict, and so that's an interesting result. The most important result of a successful proving is the meter factor. The meter factor is defined as the prover volume or mass total divided by the volume or mass total from the meter observed during a prover run. After proving, future meter readings are multiplied by the meter factor to correct for the difference that was observed between the meter and the prover. If the meter total was less than the prover total during proving, then the meter factor will be greater than 1, and the future meter readings will be increased by the meter factor. In the case where the meter total was more than the prover total, the meter factor will be less than 1, and future meter readings will be decreased by the meter factor. The main goal of proving is to determine meter factors with confidence. Two key attributes of proving data are analyzed to assess the meter factor uncertainty. These are meter factor repeatability and reproducibility. Repeatability is a calculation of how much variation occurs between meter factors that are created during multiple proving runs conducted in quick succession and under stable conditions. As such, repeatability is a short-term measure that can be calculated immediately each time a meter is proved. One very common way to estimate repeatability is to calculate the range between the highest and the lowest meter factors from a set of proving runs. The repeatability that is calculated this way is compared to a tolerance that is explained in API MPMS Chapter 4.8. The tolerance that applies to determine whether a set of proving data passes or fails repeatability requirements increases as the number of runs in the data set increases. This relationship between the repeatability tolerance and the number of runs is determined statistically to always assure a maximum uncertainty in the meter factor of 0.00027 or 0.027%, regardless of how many runs are taken. Reproducibility is a little bit different from repeatability in that it is a measure of the long-term stability of the meter factor that is found by observing changes in the meter factors from many provings taken over a long period of time. Reproducibility is used to determine how stable a meter's accuracy is over time and when flow rate and other fluid conditions are changing. Meter factor reproducibility is also used to detect when a mechanical meter is wearing out and might be about ready to fail. One of the main reasons that Coriolis meters are becoming so popular in proving applications is because they typically have very long-term meter factor reproducibility. It's easier to visualize the real advantage of the long-term stability and reproducibility of a Coriolis meter by comparing it to the typical behavior of a turbine meter as flow rate and viscosity are changing over time. So first, consider the blue peak shown. This represents an approximation of the normal distribution of meter factors about 1 that could be expected for many provings of a Coriolis meter taken over time. So there's your blue peak there. Now compare this to the orange peak that represents the normal distribution of a typical turbine meter that would be expected as long as the flow rate and viscosity are constant. Notice that the orange peak is taller and thinner than the blue peak. This shows how a turbine meter might typically have better short-term repeatability than the Coriolis meter, especially with a smaller prover, which would cause the distribution of the Coriolis meter peak to become a little bit wider. If the flow rate becomes lower, it would be common for the turbine meter to have a lower meter factor. The Coriolis meter factors, however, should not change as the flow rate changes because Coriolis meters are linear with flow rate. Similarly, if the flow rate is higher, the turbine meter factors might be higher, but the Coriolis meter factors, again, will remain constant. If the fluid viscosity changes, the difference in the meter factors for the turbine meter becomes even more pronounced. When the Coriolis meter factors continue to remain constant because viscosity has little or no effect on the Coriolis meter. Comparing the full set of Coriolis meter factors to the full set of turbine meter factors reveals the advantage of the Coriolis meter factor long-term reproducibility. When a meter factor shifts frequently, as it often will for a turbine meter, the operator has to guess what is causing the change. The operator might decide that the meter factor shift was due to a temperature and/or viscosity change and respond by deciding to apply a different meter factor for different temperatures or different product qualities. The operator might alternatively conclude that the meter factor shift was due to a change in flow rate, and in this case, the appropriate action would be to institute a policy of applying a different meter factor at different flow rates. In either of these cases, it is necessary to keep track of the flow rate and process conditions to know when to apply which of the meter factors that have been found for the meter as conditions change. One other possible cause for the meter factor shift might have been that the meter was wearing out and needed to be rebuilt or replaced. The operator must use experience and perhaps some diagnostic tools to troubleshoot and decide which of these actions is to be taken. With a Coriolis meter factor that remains very constant all of the time, this complexity is eliminated and the risk of taking the wrong action is avoided because usually no action is required. Several important challenges must be considered when designing and operating a measurement system that includes a prover and a meter. One major concern is managing the cost. Provers can be rather expensive, and especially as the size of the prover increases. Small volume provers may be advantageous because they typically take up less space than a pipe prover and are often more portable. The smaller a prover is, the less it will typically cost. However, it's not unusual for a small volume prover and a pipe prover of similar size to be reasonably close in cost. So it is important to research and compare prices. Maintenance of provers is another factor to consider. The moving parts and seals inside a small volume prover must be maintained, and the valves, sphere, and switches in a pipe prover must also be carefully maintained to avoid problems. The cost of operating a measurement system will also depend on how easily the proving is completed. If proving passes the first time every time, this can save operating costs compared to a meter and prover combination that has chronic difficulty in passing proving repeatability and reproducibility requirements. Much will depend on overall performance of the proving system in terms of this last point about proving efficiency. The pulse stability of the meter can have an impact on repeatability, especially for a small volume prover and for meters with fixed K factors, such that the pulse interpolation is necessary to achieve acceptable uncertainty. The stability of the conditions, that is to say, flow rate, density, pressure, and temperature, is very important and can adversely affect repeatability if they vary too much, especially if run times are very short. Maintaining stable conditions can be a challenge. For example, flow rate variation is very frequently caused by closing the poppet valve in a small volume prover. Before the poppet valve is closed, flow has to pass through the gap of the open valve, and this induces pressure loss, which in turn impedes the flow rate a bit. As soon as the poppet valve closes and the piston starts moving with the flow, the resistance of this pressure loss goes away, and it is replaced instead by the resistance of the piston movement and the friction of the seals between the displacer and the chamber. Under normal conditions, this friction represents much less resistance to the flow than the pressure loss through the open poppet valve, so the net effect is an increase in flow rate when the displacer launches. This phenomenon can be seen in the flow rate plot here, which shows a peak for each time the prover displacer was launched. The response time of the flow meter is also important to repeatability when the runtime is short. If the meter cannot respond quickly enough to changes that occur during the proving process, the meter factors might vary from one run to the next enough to cause a repeatability failure. Some proving systems have the flexibility to allow a different number of runs to be collected during proving. This flexibility gives operators an option to start by taking a minimal number of runs, say 5, and then either continue to collect more runs if needed or stop if the repeatability has passed. Often the ability to add more runs will increase the tolerance enough to allow a meter that first failed with 5 runs to then pass with 10 runs. One more way in which a proving system can impact the repeatability is in the way that it handles the statistical analysis of the data. Some proving systems have the computing capability that allows for calculation of standard deviation. Calculating the standard deviation reduces uncertainty in the repeatability estimate and also reduces the risk that a single flyer data point can cause a repeatability failure. Let's pause for another poll question at this point. How does your company manage the operation of the proving equipment? Do you mostly have installations where the prover is stationary, or do you maintain a fleet of portable traveling provers? Do you hire third-party proving service providers, or perhaps you employ a combination of these options? Please click the method that you commonly use and then submit by pressing the submit button when you're ready. Okay, well, we're just waiting for responses to come in and give people a few more seconds here before we look at the results. Okay, and as you might predict, there's kind of a wide range of practices out there. We can see that a lot of this work is being done by proving service providers. In fact, that was the #1 response. But right behind that, we see that there's a combination, which is not surprising because depending on the application, the way that you go about doing your proving could make more sense by doing it one way than another. And I have to comment that just in my travels around, I've noticed that stationary dedicated provers are becoming more and more common as the capacity of our pipeline systems continues to grow. So you might see any one of these out there. Thanks again for your responses. Now it's time to cover the best practices for proving Coriolis meters. To do this, we'll go over how to select the right meter size and then discuss some of the things you can do to operate the meter in a way that is likely to make proving go smoothly. Next, we'll cover considerations on how to choose the right size prover and how to operate that prover for best results. Lastly, we'll take a look at piping design and other details that can help improve the overall performance of the system. So to choose the best size Coriolis meter for a proving application, you should pay close attention to the maximum flow rate and the minimum flow rate. The maximum flow rate for a proving application is best kept below the flow rate that will result in a fluid velocity of 60 feet per second, or 18 meters per second, as the flow passes through the flow meter tubes. Micromotion has software sizing tools that are available online that are used to select the best flow meter size, and one of the parameters that is reported on is the velocity of the fluid passing through the flow tubes. So for proving applications, it is a best practice to check this value and make sure that it does not exceed 60 feet per second. These same sizing tools will also provide the zero stability number for any size meter. The zero stability number can also be found in the product data sheet that is posted on the micromotion.com website. It's another best practice to assure good repeatability to make sure that the meter size that is selected is small enough such that the zero stability will always be smaller than 0.06% of the lowest proving flow rate. Examples of the recommended proving flow rate limits for the three largest Coriolis meters from Micromotion are shown in the table. Note that it is possible to measure accurately well outside of these ranges, but for repeatable proving results, we recommend staying between these limits. Now let's discuss best practices for meter operation. The meter response time settings should be set for the fastest response possible. This is done slightly differently for different model transmitters, so it's important to consult the instruction manuals for specific details for each model. However, for all models, flow damping should be set to 0.08 seconds, and density damping should be set to 0.16 seconds. The meter zero can be important in proving applications at low flow rates. In order to judge correctly whether or not to calibrate the meter zero, you should always first use the meter zero verification diagnostic tool. This tool will tell you if the meter zero is already good or if it needs to be calibrated. All meters are zeroed before leaving the factory, so it is more than likely that the meter zero is good right out of the box and may never need to be calibrated by you. If the meter zero is calibrated, the meter should be proved. The K-factor or pulse scaling factor for a Coriolis meter can be easily adjusted electronically when you first set up the meter. The calculations shown in the box show how to compute the maximum pulse scaling factor based on the maximum flow rate you expect to see, and this method will aid you in selecting a K-factor or a PSF that will safely prevent the frequency from exceeding the capacity of the pulse counting device on your prover. If you have a pulse counter that is limited to a frequency that is less than 10,000 hertz, you should substitute that maximum frequency into the equation instead of the 10,000 hertz that you see here. Some larger meters have a published pressure compensation value and the capability to automatically correct for the effect of pressure changes on the meter. These compensations are generally very small, but they can improve repeatability and reproducibility, so it is recommended that if this feature is enabled, it should be enabled on meters that have an effect. Consult with the instruction manuals and the product data sheets for more details and to find out which meters are affected and which ones are not. One reason the response time settings are important in proving applications is because the flow signal can be noisy. Noisy flow can be caused by many things, including an overinflated proving sphere or a poor seal on a small volume prover piston. Regardless of the source of noisy flow, if the prover is sized so that the runtime is very short, on the order of 5 seconds or less, it is important in order to consistently pass repeatability requirements that the meter response be fast enough to keep up with the actual flow variation, but not too fast such that the meter response makes the flow output noisier than the true flow really is. One theory about why PD and turbine meters do not usually experience poor repeatability in noisy flow conditions is based on a concept referred to as inertial damping. Simply stated, the inertia of the mass of the rotating parts inside the meter prevents the meter from being disturbed by noisy flow. The best practice for a Coriolis meter is to ensure good repeatability by selecting a large enough prover to keep the runtime long enough to average out the short-term variation of noisy flow. We will talk more about how to choose that size of prover to achieve this in just a couple of minutes. But first, as we discussed earlier, it is often the case that there is a step change in the flow rate that coincides with the launch of the displacer. As with noisy flow, it's very important for the meter to have fast response so that the meter has caught up with the change in flow rate before the end of the pre-run. If the meter flow indication has not caught up in time, there might be a small amount of missing flow as shown in the diagram, and this missing flow can vary from run to run, causing a failure of repeatability. Similarly, if the flow rate drops during the run, the meter might over-indicate total flow if it doesn't fully catch up with the drop before the first detector switch is passed. It is even possible that the meter might miss the same amount of flow for each run closely enough to pass repeatability. The potential of this risk is that it might result in a small bias error in the meter factor that goes undetected by the repeatability check. Fortunately, a Coriolis meter can help guard against this scenario in two ways. First, because a Coriolis meter has adjustable settings to select the response time of the meter, it is possible to set the meter for fast response and avoid any missing flow from the step change. Second, it is possible to verify that the fast response setting has been successful by comparing the meter factor at different proving flow rates. In the case where the step change in true flow rate increases, then if the meter is not responding fast enough, the meter factor will become higher and higher as the flow rate increases because the meter will be missing more and more flow at higher and higher flow rates. If the meter factor remains stable as the flow rate increases, it is a good sign that the response time is fast enough to avoid the missing flow of a step change increase. It's worth noting that any delay in response that is due to the inertial damping of mechanical elements in a PD or turbine meter cannot be adjusted electronically in the way that you can adjust a Coriolis meter because the inertia is caused by the mass of the elements and not the filtering speed of the signal processing, as is the case with the Coriolis meter. Furthermore, it may not be conclusive to check for missed flow with a PD meter or turbine meter due to a step change like this by simply looking for changes in the meter factor at different flow rates the way you can with a Coriolis meter, because the meter factor for a PD and a turbine meter might already be changing at different flow rates for other reasons, such as meter nonlinearity or process condition changes. Ultimately, the best practice is to ensure that the prover size and operation are such that the pre-run is of adequate duration and the step change in flow rate is small enough to avoid altogether the potential for missed flow. Micromotion meter diagnostics include a feature called Smart Meter Verification, or SMV. The SMV diagnostic tool allows you to check for the health and accuracy of the meter in place. And it could not be easier because it does not require you to do anything before running the test. You don't need to interrupt the flow or control any process conditions. The flow measurement from the meter itself is not even interrupted by this process. SMV is a powerful troubleshooting tool that also allows you to do frequent testing in between proving while your system continues to run. It improves safety and reduces travel time by allowing you to troubleshoot without having to send someone into the field. And once SMV has been purchased and installed as part of the meter, there are no additional costs to run a test, so you can run as many tests as you want, as often as you want, without incurring additional cost. I should pause here and remind everyone that Coriolis meters are extremely unlikely to be damaged or change or drift in service, so the expected results of the SMV test are almost always going to pass with no trouble found. Now, the table shown here includes information to help select the size of a small volume prover to prove a Coriolis meter. To use the table, start by finding the flow rate on the left side that is closest to the maximum flow rate that will be used to prove the meter. Next, choose the column that fits your plans for the number of piston passes you plan to average per run. If you only plan to use single passes as runs or 2 passes per run, use the left column. If you plan to average 3 or more piston passes per run, then use the right column. The volume shown in gallons in the column you are using that corresponds to the maximum flow rate for the application is the minimum displaced volume that is recommended for proving Coriolis meters. We recommend that you choose a prover size that is equal to or larger than the displaced volume indicated. The longer the prover run time is, the better the repeatability is likely to be. One other consideration is to ensure that the prover size is large enough to prevent cavitation inside the prover. The vapor pressure of your fluid and the velocity and pressure drop through the poppet valve will be the factors that are most likely to help you estimate the risk of cavitation inside the prover. In order to ensure the best chances for passing repeatability when proving a Coriolis meter, one of the most important areas to focus on when operating and maintaining the prover is how to maintain a stable flow rate. Good maintenance on the prover, including internal seals and attention to the proper inflation of pipe prover spheres and plenum pressure, will help to ensure smooth flow through the prover during proving runs. It is important to ensure that back pressure is sufficient to prevent cavitation in the prover, but especially just before the launch of the displacer. If the prover is located where extreme weather conditions may exist, insulating the prover can improve meter factor reproducibility. If the prover has selectable detector switch locations that allow you to increase or decrease the runtime and the pre-run, we recommend a setting that maximizes the runtime. Results seen in field testing that we have done are generally more positively impacted by longer run times than they are by longer pre-run times. As mentioned earlier, it is possible to verify that the pre-run time is long enough by proving at different flow rates and observing to see if the meter factor changes significantly. If no significant change is observed, then the pre-run time appears to be long enough. If you observe a significant change, then increasing the pre-run time should help. There are some decisions that can be made according to API MPMS Chapter 4.8, which have the potential for improving repeatability. Calculating the standard deviation instead of using the range between the highest and lowest meter factors to measure repeatability is more accurate and less susceptible to repeatability failures caused by any single flyer meter factors. Averaging multiple passes per run also helps to reduce the uncertainty of the repeatability measurement that can be caused by a combination of noisy flow, short run time, and fast meter response. We recommend 3 passes per run when using a small volume prover at flow rates that result in a run flight time of 5 seconds or less. When proving the range between the highest and lowest meter factor to estimate the repeatability, more runs will allow a larger tolerance. For that reason, we recommend starting with 5 runs and a 0.05% repeatability tolerance. If the proving does not pass, we recommend increasing the number of runs to 10, which increases the repeatability tolerance to 0.12%. Increasing the number of runs and the repeatability tolerance does not diminish the confidence in the meter factor. Instead, it reduces the uncertainty of the estimate of the true statistical repeatability. The piping between the meter and the prover should be designed to help maintain stable conditions and flow rates while proving. This is true because one of the fundamental assumptions underlying the concept of proving is that the exact same quantity of fluid passes through both the meter and the prover simultaneously. One precaution that can help ensure this is true is to make the distance between the meter and the prover as small as possible. Furthermore, valve locations and piping paths should be designed with an eye on avoiding long dead-end branches in the piping between the meter and the prover, where vapor pockets can be trapped or compressible fluids can be squeezed, creating a volume spring that allows for a total liquid volume contained in the piping to change. The back pressure on the entire system should be high enough to prevent any cavitation anywhere in the system, including in the meter. All associated prover equipment, like temperature and pressure transmitters, need to be kept in good working order with up-to-date calibration documentation. When a pycnometer or density meter is used to prove inferred mass units, it is very important for the pycnometer or meter to be located close enough to the prover so that the pressure and temperature in the pycnometer are the same as the pressure and temperature in the prover when proving runs are taking place. Finally, it is essential to ensure that all valves that are intended to be shut are actually fully sealed with no potential for leaks. To conclude, I would just say that the best practices we have shared today are intended to help you achieve the best possible proving results with the least amount of trouble and cost when proving Coriolis meters. Our intent is that you will find that with these, you can use Coriolis meters in more applications and with greater confidence than ever before. The benefits of successfully installing and operating micromotion Coriolis meters in a custody transfer application begin with the long-term stability of the meter factor. When the meter factor is stable, everything becomes easier, and so it is worthwhile to learn how to pass short-term repeatability requirements with ease so that you can then move on to enjoying the real long-term benefits of maintenance-free operation and constant stability that a micromotion Coriolis meter will deliver. So thank you for attending the webinar, and thank you for sharing your responses on the 2 poll questions. At this time, I'll turn it back over to Allison, and we'll jump into the question and answer session.
Great. Thank you so much, Mark, for this great presentation and all the great information. We would now like to open it up, like Mark just said, for any questions. So please use the Q&A chat panel to ask the questions. And Mark, we already have a folder full of questions waiting for you. We decided, everyone, just to put them to the end as we were running a little late. So Mark, I think you should just jump on in. And just as a reminder to everybody, we have more questions than we're going to be able to get to today, but don't worry, Mark will personally answer all these questions. And so again, if we don't get to your question today, please don't worry, Mark will follow up with you. Mark?
Okay. One question that we received is how much two-phase mixture of liquid and gas flow can a Coriolis typically handle and still measure accurately? This is a difficult question, and I'm going to answer by saying we typically would not expect to see any two-phase flow in a proving application, not just because it's typically not allowed, but because the prover itself and the volume of the piping between the meter and the prover would be suffering from any kind of compression of the gaseous phase. So in applications where you're not proving, there's some ability of the Coriolis meter to measure two-phase flow, but in proving applications like we're discussing today, every measure should be made to try and eliminate as much risk of two-phase flow as possible. Okay. Okay, one other question is, should dampening on a Coriolis meter be set to 0 when proving with a small volume prover? In past guidelines that we have issued and in past practice, we've often recommended setting the damping to 0. We're revising that recommendation to setting it to 0.08 seconds for future starting point, mainly because the difference between 0.08 and 0 is very small, but just a tiny bit of damping actually helps to reduce repeatability variation in testing that we've done more recently. So you still have all the advantages of the very quick response in terms of being able to do short runs and short passes without fear of the step change and noisy flow problems I talked about. But you also avoid having too much noise with too little damping that can be possible in some applications. I have a question here. It says, how sensitive is the Coriolis meter to transporting it from site to site when used for proving? And I think this means when used as a master meter for proving. And I would say Coriolis meters are actually designed in such a way that they can be transported very easily. And the only thing that you want to be sure to check when you use a Coriolis meter as a master meter and you're transporting it probably is the zero. And the zero verification tool is a very easy way to ensure that in transportation the Coriolis meter has not seen any kind of zero shift that might impact the proving. I have another question here. Does a Coriolis meter in long-time service need to be proved after a zero is performed? And that actually is written into the MPMS Chapter 5.6 that you do need to prove the Coriolis meter after zeroing, because there's a potential, depending on the flow rate, that you may have introduced a slight change to the meter factor through the zeroing process. Here. Just need to give me a moment here to catch up on some of these. Yeah, I did have a comment, not a question, that I made a reference to a density correction factor used to convert, and I'm being told that that's a density meter factor. So I think these two terms might be used in conversation, but the thing that's important to keep in mind is that when you convert from a volume prover reference to a mass total for proving a mass flow meter, you definitely need to have a very, very accurate density conversion factor.
Well, just so everyone knows, Mark's reviewing. We are getting a phenomenal amount of questions in. We have nearly 70 questions sitting in the queue, so he's just reviewing them all. And like I said, don't worry if he doesn't get to it today. He will get you a personal response back. And Mark, sorry.
Yeah, thank you, Allison. That's true. In fact, we have this problem because of the limited time with the webinar series that sometimes we get more questions than we have time for. So if we don't get to your question, we will definitely get back to you as quickly as possible with a written response. And we'll try to make sure that we also locate your micromotion contact so that they are also aware of your question. I have a question here. About whether Micromotion would recommend a pipe prover or a small volume prover, and we don't recommend one over the other. The intent of these guidelines is to provide information that should give you best practices to work well with either. We recognize that you may have many different overriding factors that would help you with the decision between a pipe prover and a small volume prover. So our goal is to give you the information you need to make the meters work well with either type of prover. Okay, I have a question here. Can you tell me how much deviation in meter factor would be acceptable over a long time, say a couple of years? Typical process conditions are C2 plus liquids at 440 kilograms per cubic meter. You'll actually find that this is not specifically specified in the API MPMS, and it's left up to the agreement between parties in a contract. You will find references in some federal regulations and other areas that make reference to 0.25% range as a typical acceptable variation for meter factor over a long period of time. But I will tell you that I know other applications, especially in the downstream side of things, where customers are successfully proving with a plus or minus 0.05 variation allowed on the meter factor long term. So I think it depends on your installation and the product fluid and the conditions that you're operating under. But in general, the answer I've seen in a wide range of different applications is usually somewhere between 0.05% and 0.25%. So I have a question here. Are you recommending that a single pass be 2 seconds for a small volume prover? And yes, actually, if you look at the sizing table that we covered for selecting a small volume prover size, and you work out the math, you will see that most of those reflect back to a size in terms of the volume that would give you 2 seconds or more per pass. This is what we're finding in the most recent testing that we're doing, both in our laboratory and in field tests, to be a fairly conservative approach that is the best starting point to ensure that you have good repeatability right out of the get-go. Now, you might see good repeatability with shorter passes in certain types of conditions and installations, but these are the recommendations that we make to give you the best chance of ensuring that you don't have problems with repeatability from the very beginning based on a wide range of different applications we've seen. One thing I would add is that you'll also notice that if you take more passes per run, we're adding those passes together for a total run time, and that same target is 2 seconds there. I want to mention that we have in preparation a proving best practices guidelines that we intend to make available on our website in the next week or so that includes a version of this table. So you will be able to see that, and that will include the equation that shows the relationship here as well. We need to wrap it up because we're just about out of time, and I just want to reiterate that we will get back to you if we didn't get to your question. We capture all of these, and apologize to anyone whose question we didn't get to, but I just want to thank everyone one more time for joining us. Really appreciate it. Hope you got a lot out of the webinar, and I'll leave you with some contact information, including my email address, and we will, as I mentioned, be publishing the guidelines that are related to this webinar on our MicroMotion website in the very near future. Thank you.
Great. Thank you again, Mark. And if anybody thinks of any additional questions after the webinar, you can email Mark at the email address that he's showing here on the screen, or you can actually click on the Contact Us button on the bottom of the bar in your webinar console, and please just don't hesitate to ask questions. As Mark mentioned, we do actually have a very large number we didn't get to on the webinar today, so he will personally respond back to you. And again, we want to thank everyone for joining us today and for all these amazing, great questions. As a reminder, we will be sending out an email with a link to the recording tomorrow, along with a list of some additional resources on this topic. On behalf of our guests, Mark Butler, as well as everyone at Emerson Micromotion, we thank you again for joining us and taking the time to view this presentation, and we hope that you have a great day. Thank you.